Have you tried connecting a large language model to the internet or to an API? Maybe you're building an AI-enabled app that needs access to real-time market data. Or maybe you need to query information from a customer database. The way to do this is through a technique called tool use or function calling. In this video, I'll show you the most robust approach to integrate an LLM, namely using GPT4o-mini. I'll then show you the fastest and lowest latency way using Groq's API. And lastly, I'll show you the most robust way to integrate tool calling within open source language models, including if you want to run one on your local laptop. If you're new to tool use, I'll show you all of the steps needed to get reliable results. And if you're a little bit more advanced, I'm going to show an example where I am doing tool calling with a zero-shot 3.5 billion parameter model that I've quantized to 4 bits and have running here on my Mac. All right, for the video, a few different sections. I'll start by talking about how to set up tool use. And yes, if you're here for Trelis research, you're here for the nitty-gritty. So I'm going to go through a process flow diagram that'll hopefully be high level, give you a picture of how tool use works. I'll talk in quite some detail about setting up function definitions. And I'll talk about building the metadata and the list of tools. This is pretty important if you want to get robust systems that will report proper errors so the language models can handle those errors and hopefully get the next iteration of the tool call correct. We'll see more about that in a little bit. Then I'm going to move on to querying the LLM, and I'm going to show a few demos. So I'll show how to do GPT4o-mini, which is a fairly recent model that has come out. It's very cheap and not quite as good as GPT4o, but much better than GPT 3.5 Turbo. It does have tool use as well. Then I'll go through an example with Phi-3. I'll go through the Phi-3 mini model. It's really quite a small model and performs surprisingly well with zero-shot function calling. Then I'll go through an example using the Groq API. Groq does have a model for tool use. We'll see how that performs. And then I'll show a quick example using Groq with, rather, I've said this backwards, but I'm going to show you first the zero-shot example with Groq, and then I'll show you how the fine-tuned model performed. And I think you'll find that comparison interesting. And last of all, I'll go over a few final tips as per usual, and maybe give you a bit of background on this video. It's one of the more fun, well, a lot of them are fun, but one of the most fun videos I've made for reasons that you will soon find out. So let's start off with a diagram here of tool calling and function calling. These are basically the same thing. OpenAI originally called them function calling and everybody else did, and then they introduced tools, which in principle can include things other than function calling. But really one of the main use cases is function calling. So here's what we're doing. We're taking in a piece of text, an input question, like where is the weather in Dublin? And our goal is to get an answer to that. And because the weather in Dublin is something real time, the language model is not going to know that naturally, and therefore would benefit from being able to access outside data, maybe from weather.com or maybe from, say, a Bing search. So the idea is to provide the language model with access to outside information via retrieving functions. Here I've got 2 functions that I'll also use in the later examples. One is a simple function, you can imagine for now, for getting the right clothes to wear given a certain weather condition. And the second function is getWeather, which simply will give you the weather if you input the city in which you are in. So the starting point for tool use is a prompt or a set of questions, and then a set of functions which allow us to connect to APIs. And in this case, I'm just using some dummy functions that will give back some arbitrary weather given Dublin or given New York or any city. But in practice, you could hook this up to a live API so that the real data is flowing back. Now, of course, what we're going to use to answer this question is a large language model. And the 3 examples I'll go through are using OpenAI, using Groq, using Runpod to run Phi-3 Mini. And also, actually, I should write it in here. I'm going to run locally on my laptop using Llama.cpp and a quantized Phi Mini model. So after we have the prompt and we've defined the functions, we're next going to flatten those functions into what's called metadata. Now, the reason for this is because the language model is going to need an input of the text But we also need some structured way to say to the language model, here are the functions or tools you have access to. And the structured way we do that is the metadata. So the metadata is essentially a flattened form of these functions. And I recommend programmatically generating this metadata from the functions themselves. You can write this up separately, and I would say it's maybe not uncommon to do that, but I think you will get much better reliability if you have a script that will take in your functions and flatten them into metadata. That means you can focus on writing very clean functions, and you can rely on the script or errors from it to tell you whether the metadata has been generated systematically. Okay, so we have the input prompt and we have metadata, so the language model knows what functions it has access to. So with that in hand, we're going to build a prompt, and I'll just increase my screen size here. So the prompt is very simply, I'm giving this at a high level, but what's happening here is we have metadata. So we just inject this metadata here, and then we put the prompt afterwards. This is how function calling works. And that prompt then, which includes a list of functions available, goes into the language model. And the language model then, if it's been trained to return function calls, or if it's been a zero-shot prompted, which we'll see later, if it's asked a question where it would get a better answer by availing of these API calls or functions, it should respond in a structured way. So it shouldn't respond the weather is great or the weather is sunny. It should respond with a request for more information from these base functions over here. And this here is going to be a structured object. Typically it's structured as a JSON object or an array of JSON objects if, for example, the language model wants the weather in multiple places like Madrid, Paris, Dublin, and we'll see more about parallel function calling later. For now, I'm just showing one function call here, and I'm simply representing it as, okay, we're going to call the weather function, and we're going to call it for the city of Dublin. So next, what happens is we will have a piece of code that takes that function call, so it takes this JSON here or array of JSONs, and it will send them to another program here that will simply list through the functions that are available, see if any of the ones available match the ones being called. So here, the weather one, I should really have written get weather here. Let's see, maybe I can, it's only going to appear on one slide, but I should really have written get weather there. So what it's going to do is match that we have get weather, and it will call that function with the city of Dublin to get a response. And the response in this trivial case is 15 degrees, good summer balmy weather here in Dublin. So now we've got this real-time data, and we're going to feed it back into the language model like this. And with that data fed back in, hopefully the language model will give us a nice clean sentence at the end saying it's 15 degrees C. Now, to be clear, I've shown one language model here and I've shown two steps. These steps occur separately. So there are two separate calls made to the language model. The first asking the original question with the metadata, and the second one here, which incidentally will also have the metadata within the prompt, and the language model should know that it doesn't actually need to make another call because now it's being provided with the information. So we see exactly how those prompts are being structured, but for now, note that there are two steps at least. There's the initial question, there's the retrieval then of further information that gets passed in for a second call. And in some cases, if for example we wanted to get the right clothes to wear in Dublin, that would mean there are three calls, because there would be first the question, what clothes should I wear in Dublin? Then the language model should request information first on the weather. And when the weather comes back at 15 degrees, the language model should then ask for the right clothes. So that will be the third, that will be the second call rather. And the third call will be taking the information on the clothes and getting the final answer, which should be wearing, I don't know, a jacket or trousers and something like that. So this, in brief, is a look at tool use or function calling as a schematic. And there are a few critical parts to get right if you want the performance to be good. So the first one, and probably one that's I've talked a lot about on this channel previously, is you need the language model to be good, and you need it to know, okay, I've got this prompt here and I've got weather information available. I should be making a function call. I should not be responding with the hallucination that the weather is 16 degrees. Further, it should be able to know that when I send it back the information, for the next prompt, it should be able to look through the prompt history and it should answer reasonably it's 15 degrees C and not just keep calling the function to get the weather or not accidentally call a function to get close. And we'll see that in some examples later where things are not quite working as they should. But what I'm saying here is the language model needs to perform well. The other thing that probably is a bit overlooked or maybe not talked about so much, or maybe it is and I'm unaware, is preparation of these functions here. It's valuable if you set them up in a way where it's very clear to the language model what the inputs are. Are they strings, integers? What the outputs are they strings, integers? And also what some example values are. So there's a little checklist I want to show you in building up your functions. And then there's an approach I recommend for converting from functions programmatically to metadata. So here are some quick do's, and we'll jump then into an example. Some do's on defining functions. Do define the types. So when you describe a function for getWeather, make sure you say which of the inputs are integers, which are strings. Do include a description. I'll show you that in VS Code. Do return a dictionary. So functions, of course, can return many types of objects like strings or integers or floats. I like returning a dictionary though. It keeps the structure consistent so that there are always the same rough objects or the same objects being returned. And I think consistency is always something to strive for if you want to improve the quality of outputs of a language model. The third one here is validation. Validate that you are getting the inputs that you expect. For example, if the language model calls the getWeather function and instead of giving a place, it gives an animal name. Now, that maybe you've got a list, for example, in the function of valid cities. And so if it puts in dog, it's going to say, no, that's not a city. And you want to have as much validation as possible within the function. And you want that error, if there's an error, to say something sensible like, that was not a city. Because if you send back useful information, it's possible you'll get the language model automatically on the next iteration. And we'll see how recursive loops can be built in. You can get it to kind of self-correct. So error management and validation is very important. And as I've said a few times, you'll be tired by the end of the video, generate the function signature or the metadata. That's the input that goes in with the prompt. I think you want to generate it programmatically from the functions rather than writing it out separately where you separately define functions and you define metadata. That's kind of a recipe for inconsistencies. And as a bonus, do make sure that you avoid infinite loops. If there's a risk of a function that you're using taking a very long amount of time, it's a calculated problem, you might want to impose a time limit on it to make sure there's a timeout. And then there's a sensible error going back saying, hey, there's a timeout if you want the most robust system. So I'm not going to go to final tips because that's for the end of the presentation. What I am going to do is dive into VS Code and some examples. The repository I'm going to be working out of is the Trelis Research Advanced Inference repo. Now, hopefully just by watching the video, you'll be able to grasp most of the high-level points and just implement them to yourself. But if you do want to follow on, you can purchase access to the individual scripts by going to trelis.com/advanced inference. I'll put the link below. And this repo, by the way, contains many of the scripts from past videos you also might be interested in. It contains, for example, Monte Carlo methods of improving the answers during LLM generation. It includes the privacy video where we redact sensitive information before sending it to LLMs like OpenAI. It includes a section on server and API setup. Let me just scroll down on that for setting up Runpod, VastAI, Llama.cpp, that's on your laptop, or even serverless deployments on Runpod. And then it has a series of API call folders, including just simple API calls to different endpoints, function API calls, which we'll be talking about today, speed tests, data extraction if you want to extract entities in JSON or YAML form, and then an advanced RAG technique that I've called AllSort, and you can check out that video. So we'll be working out of the folder that is in API calls and is then in function API calls. And what I've done is open that up in VS Code. So let's head into API calls, function API calls. And first, let me show you the function metadata, which I have stored under functions and tools.json. So this is what you put in right before the prompt. So you have the prompt, the question that you want to ask, what city, what's the weather in Dublin? And the metadata is the structured way of telling the LLM what it has access to. And this is programmatically generated in my setup from the function calls. Now, just to give you a look at what this looks like, here we have two functions. We've got getCurrentWeather and we have getClose. And you can see the function metadata, it's an array of JSON objects. So we have a JSON object for each of these functions. And the JSON object for each function has a description. And I can show you here the full description. It has parameters. This means the inputs that the language model needs to give if it's going to call the function. And it also has a list of the required parameters. So it's telling the language model which ones it must provide. So it definitely has to provide location, meaning the other parameters like unit here, which is the Celsius or Fahrenheit, that's going to be optional. As you can see, there are default values provided as well where appropriate. So for example, the default here that will be called by the function is just Celsius if that's not specified. Now getClose is similar. It's going to take in inputs of temperature and condition. Condition is like cloudy or that kind of non-temperature type weather parameter. And again, you've got the list of required parameters. Both of them here are required. So this is the structure that's used actually if you're going to query the OpenAI API, and I've kept the structure the very same if you want to query Phi-3 with zero-shot function calling, or if you want to query Llama.3 with zero-shot function calling. And that's what we're going to use for hitting the Groq API. Now, if you want to use the function calling models on Groq, which I'll talk briefly about, then this syntax is slightly different. It's actually not an array. So you get rid of these square brackets and you just put a new line between the JSON objects. So there would be no comma there, and we'll get to that later. But I want to show you how I create the functions and then how I flatten them into this format. So let's take a look at those original functions, and I'll highlight some of the points I said are important. So first of all, when you define a function, make sure you define the type. So here I'm saying temperature is a string. Now, probably would be better to do that as an integer. I've done it as a string and I've done some validation on it. The reason is because I want to allow the temperature to be specified as 15F or 15C. I guess it'd be like 70F or 15C or whatever the equivalent is. And I've defined also that the condition is going to be a string. The reason you want this is you don't want the language model to respond in a format that the function is not expecting. Here in these triple apostrophes, I've put in a full description. And I like putting in a description not just of the input parameters, but also of the output, because this gives context to the language model on exactly what it can get. What useful information can it get from the language, from the API? So rather than just kind of leaving this empty, I think it's important to put in a full description. And you'll see later when we squash this into the metadata, I'm going to specifically extract, I think it's the doc property that will grab these comments here. As I mentioned earlier, providing examples is useful. So here I've given some examples of temperature. I've given some examples of the condition. And this again increases the chance of the language model responding correctly. Next is another tip here, which is the validation. So you can see if my input is not a string for the temperature, or if there aren't two pieces, and there have to be two pieces because it's 15 space C or 15 space F, then it's going to tell, it's going to respond and it's going to return this here, which is invalid temperature input. Please provide a temperature in the format of XXF or XXC. And this helps error correction because it means if the language model gets it wrong, there's a good chance it's just going to recall in the next loop and it might actually get it right. Here, I just have some logic for handling Celsius or Fahrenheit and some more error handling if they're invalid values. For example, you could bound the range on the temperature. If they put in like -200, that's probably not a temperature that's relevant for a real city. Here, I've got validation on the condition. And this is just my way of giving some kind of manual answers to what the weather would be. In practice, this would probably be calling a weather API to get real answers. And then last of all, notice here how I'm returning a JSON. It's a dictionary that contains outfit and then the actual recommended outfit. And that's important because, again, it means every function is going to give the same dictionary. It may not be exactly the same contents, but it helps add consistency. And I won't go through the getWeather function, but you can see the same attributes here, like a description, like having some validation, having some error. Do I have some validation here? I don't. So that's an area for improvement on this. I could definitely do some more checks, and that would probably improve performance as well. I do, however, have a nice error message here, and you can see my error message is nicely wrapped as a dictionary. That's something I probably should do as well for get close. Make sure the error is being returned as a dictionary as well, so all the formats are going to be consistent. With that, I'll show you how to flatten these and convert them into tools.json. That's done using a script here called function utils, and it contains a function to convert from functions to metadata, which is what we want in tools.json. So what it's doing is it's inspecting the signature of the function. It's getting the type hints, and this type hints, by the way, refers to whether it's integer or string. So it's the type of the inputs that we're using. And it's going to take this information and inject the parameter type and inject the parameter names into a structure, a JSON structure that we want to print as tools.json. And you can see here a little bit how it's prepared. It matches tools.json. So every tool we have is going to be function, then the name of the function, the description, which you can see here is pulled from that doc attribute. And then you'll have each of the input parameters that are being provided. Now, something I'm not doing here, but I think is probably worth thinking about, is adding in a returns schema. By adding in the return schema, you're again giving more structured information about what the model can, about what the API can return. To some degree, that's captured if you have a detailed description that includes what is being returned, including the type that's being returned, a string here. But perhaps a more structured way would be to do it via a returns type parameter and dictionary here. So just a little extra tip you might want to dig in on. So once we have a function for converting function to metadata, really what I mean there is we have a way to convert to this JSON object. And then we need another function that will put the JSON objects together within an array of JSON objects. And that is what is happening here with prefer function tool calls. It's going to iterate through the functions directory, find any function that ends with py or any script that ends with py, and it's going to then convert that function into metadata JSON, and then it's going to put those metadata JSONs together within an array of JSONs, and that will allow you to generate the tools.json file. Now, I do have a few other functions here that I'm not using. These relate to determining the type and the name of the return values, which I said is an interesting thing to consider, but not something I'm doing right now. So let's, you can run this script. If you do run it, it's just going to run prepare function tools, which in turn will run twice the function to metadata, because we have two functions located here. Sorry, I might have been pointing to the wrong files earlier, but I meant point to these two function files here. And when we run it, and by the way, I'm going to run that at the very start of every call I make to the LLM, just in case there have been changes to the tools that I want to select. And that is going to result in a flattened tools file like this. And by the way, because this is an array of JSON objects, we're able to do json.dumps. You'll see that later in the script in order to flatten that into a single string. So yes, everything that goes into an LLM needs to be converted into a string, and it needs to have the proper escaping as well. So json.dumps is a way that we convert this array of JSON objects into a single string that will then prepend. It will prepend the prompt that says, what is the weather in Dublin? Let's recap a little bit on where we are with the help of our diagram. So I've described what have I described? I've really described how to take functions, put them in a folder, and then automatically flatten those functions if they're well defined into metadata. So we have metadata now, and the next step is I'm going to show you a script that will take in metadata, take in input text, create a prompt, send that prompt to the LLM, then then take the function call, execute any function calls required, and send them back to the LLM. And what you're going to see is a recursive loop. So I'm going to keep on looping around. So long as the language model keeps calling functions, I will always execute those functions and send the information back. And I will only stop that loop if the language model gives a response where there is no function call. Now, to stop infinite loops, I have a max recursion depth, which I'll usually set to maybe 3 loops, which allows for 2 layers of function calls. You could set it a bit higher if you wanted. but that stops infinite function calling loops. If you have a model that keeps calling functions, then this is not going to work. So you need a model that's going to be strong enough, either fine-tuned or zero shot, to be able to make sense of the information you're giving back. So hopefully it will eventually give a useful answer. Okay, so that script it's present in a few forms. I've got a form for doing OpenAI function calls using GPT4o-mini. I have a function for doing function calls to Groq, and I have one as well for zero shot. And I have one as well for zero shot with parallel function calling. That's where you can say, get me the weather in Madrid and Dublin, and it will do both at once with a total of only 2 calls, one to get the function call and one to kind of coordinate that information and answer what the weather is like in both locations. But first, I'm going to describe the OpenAI type script. I'll just work top to bottom here. This script here is just a 2-step script, so it makes a first call and a second call. I don't have the loop happening, so it'll provide a basis to explain how it works, and then I'll show you with the recursion loop. So first thing I'm doing here is I'm importing the prepare function tools. That is what allows us to flatten to metadata. And then I run this function, which literally creates the tools.json file. Next, I'm going to load a model that we're going to inference. And for the case of OpenAI, that's going to be GPT4o-mini. And I'm going to set that in the environment variables. Now, it's easiest so I don't expose my own environment variables to look at the sample.env file. And you can see up here, I need to specify a few things. So I need to specify the OpenAI endpoint, api.openai.com. I need to specify an API key, which I get from OpenAI. And I need to specify the model, which is GPT4o-mini. Okay, so I've set my environment variables. I've set the model. I've set the API endpoint. The actual endpoint to hit needs to append /v1. So I've done that here. And here I've set the API key. And now I'm defining the client. This is from the OpenAI library. We'll actually be using this library in all of the cases. So every one of my examples today will be an OpenAI style endpoint, including when I run it on my laptop. Next, we're going to open the tools.json file. That's the flattened metadata file, so that we can import that and put it in the prompt. We're then going to import a list of functions. So what I'm doing here is importing the functions I have, get close and get current weather, so that we can execute them later. And I'm programmatically doing this for all of the tools that are within tools here within the JSON metadata. Next, I'm defining how to make a chat completion request. This is a call to the API. I have a few inputs. I have messages, tools. This is going to be the metadata that we're going to pass in. Tool choice. This is a parameter that OpenAI expects. It can be set to auto if you want it to automatically decide whether to call a tool or to give a normal response based on the answer, or you can actually force it to pick a specific tool, in which case it will definitely give a tool response. Typically, I set it to auto because I'm working on cases that may or may not need a tool call. And then we also need to pass in model. So these all go into the chat, create client chat completions, model messages. I like setting a low temperature. That may not be optimal, maybe use 0.3, 0.5. Then I set max tokens in the response. Tools here is going to be the metadata, and tool choice will be set to auto. It'll be set later on. Next, I have a little script to actually execute a function. So every time there's a function call that needs to be executed and we need to fetch the data, it will call this, and it will do so by taking a message, which will be the function call itself message, and also a dictionary with the functions, because we need to know which functions we want to actually execute. So here we're going to extract the first tool call from the tool calls, the message that the language model provides. So the language model will respond, and it will either respond to call 1, 2, 3, or so many tools. I'm just going to look at the single tool case. It will take that first tool call, which will just be the first tool, and I'm going to extract the function name, and I'm going to extract the arguments. The arguments are needed for inputting to the function that we're going to call. So here we're loading the JSON of the function arguments. And then for every function that's in the input functions dictionary, so if there were 3 functions, it would repeat this 3 times. It's going to check that the function arguments exist, and then it's going to call that function. And it will do that by finding the function itself via its function name in the functions dictionary and then passing in the function arguments. And these two stars here just mean that it will expand out. If there's an array of arguments, it will expand them out and inject those arguments to the function we want to call. And notice how I have some nice error handling here, so that if it goes wrong, hopefully the language model might be able to correct, or there's some way to maybe avoid calling that function on the next iteration. And if all goes well, we'll return the results. And we're also going to return the JSON, which will represent the tool call itself. And the reason I do that is because we want to send in a series of messages to the language model to get the next answer. And that series of messages should have the answer to the function call, but also it should have the function call that it made. So we need that to be included in the history for the language model to understand the full history and give the right answer. Next, I have a formatting function. This is just a way that I output the chat in the terminal. Just helps me to visualize different colors for assistant and for tool calls and for the user message. Okay, so here we get to the recursive step. Sorry, I said this would just be two-step, but I forgot I'd have updated all the scripts to be recursive. So let's take a quick look at how this works. So first, we set the recursion depth at 0 to start, and we set a max recursion depth. So there'll be a counter on each iteration, and once we hit 4, that will stop, so we don't infinitely call functions if it's stopped in a loop. The first thing we do is we get the chat response. By the way, this is the check here to see we haven't exceeded the recursion depth. Then we get a first response from the language model, often a tool call if we're asking for the weather. It will check that the chat response exists. And if it does not exist, this line here checks that if the chat response is an exception, so there's an issue, then it's just going to exit this loop and return the messages as is without adding any further information. However, if the chat response is valid, we're going to extract, and this is just following the OpenAI docs, we're going to extract the assistant message, and then we're going to check if the assistant message is a tool call. Now, if it's not a tool call, we're going to skip all of this and go right to appending it as an assistant message, and we're going to leave the loop and just return the answer. So if I ask, how are you today? It's going to say, oh, I'm an AI and I don't have feelings or something. And that will not be a tool call. So it means we will just append the assistant message and we will leave that recursive loop. But if we call it tool, then what we're going to do is we're going to execute the tool or the tools if there are multiple. And by the way, this script is just for single tool at a time. I'll show you parallel later. So here we execute the function call with the assistant message and the functions. And we get back the results. And you'll remember that function that executes, it gives us the results and it gives us the input tool called JSON. So here we're going to append the assistant message. This is to tell the language model on the next go around that there was actually a tool call made. Then we append the response to the tool call, which comes from the execute function call. We're going to put in the tool. We're going to put in the tool call ID, and OpenAI will generate a tool call ID. So that's why we can access it via toolcall.id. In zero-shot function calling, I won't have the language model generate the IDs. I'll actually programmatically generate them, which I think is a little bit more robust. But either way, for OpenAI, it will generate an ID. So we provide that ID as part of the function response. And the reason we provide that is so the language model can associate the ID of the call with the response. So this helps particularly if there are multiple functions being called at once. Then the name of the function being called, and then the results of that executed function call. And with all of that done, we then move to the next iteration. So you can see here that what I'm returning is actually a callback to the same function. So it's looping on itself. And that loop is just going to take in the messages that were created and appended to in this loop. So you can see now, because we're incrementing the recursion depth, what's going to happen is we will keep looping through this chat completion request recursive until we hit the recursion limit. And at that point, hopefully we'll have gotten an answer that's not a function call. But if we did get an answer that's again a function call, it's just going to return and avoid infinite looping. Lastly, down here, I have a simple piece of script that will initiate an array of messages. And then it just allows me to select a few different queries that I'm going to run through. And you'll see why I choose these four, but I'll run through them all for all of the scripts so you can get a clean example. Then it takes those messages, submits them to this chat completion request recursive. with the tools metadata, and then it will just print out the messages. I'll print them in raw form, and then I'll print them in pretty form as well. So let's run the first question. And the first question I like to test is always a non-function calling question. What is 1 plus 1? And we're hoping here it doesn't call a function. So let's see what happens. Let me increase this and scroll up. Okay, 1 plus 1 equals 2. And you can see in raw format, we have role user, what is 1 plus 1? And we've content 1 plus 1 equals 2. And that's from the assistant. And there's no function call and there's no tool call either. Next up, what is the weather in London? Keep in mind, we do have access to a get weather function. So we expect one tool call here. Okay, so we have what is the weather? We have a tool call with the location of London. That's the input required. You'll remember that the Celsius is optional, so that means it's being called with Celsius because that was made the default if it's not specified. So get current weather, 15 degrees and cloudy. The current weather is 15 degrees and cloudy, so great, great. Next question. The current weather in London is cloudy with a temperature of 15 degrees. What clothes should I wear? So again, it should be relying on the get weather function, on the get clothes function, and it should be inputting that temperature and condition. So let's see how it does. Okay, get clothes calls get clothes with temperature and the condition of cloudy, gets back the outfit, and then it recommends long sleeve shirt and jeans. So that's perfect. And the last question, which is the trickiest of these, is the chaining question where I ask, what clothes should I wear? I am in Dublin, which requires the language model to first of all get the weather in order to then get the clothes. So we'll ask that question and see what happens. Okay, so this is great. What clothes should I wear? It gets the weather. It uses that information to then get the temperature. Get the clothes. You can see the temperature 18 is input here. The condition is input here. And that gives the outfit, which then allows the answer to be in Dublin. You should wear moderate clothing such as a long sleeve shirt and jeans. Good general advice as long as you bring a brolly as well for Ireland. So this is great. And this is GPT4o-mini. And it performs really well. It's quite robust. It's a relatively cheap API as well. And so I'd probably recommend this as your first port of call, unless you want to get really high speed, which I'm going to show you using the Groq API. Before I do that though, let's take a look at the script I've developed here for zero-shot function calling. And actually I think I can just run this script with Groq, but first I want to run it with Phi-3 Mini, which is a small model. I think it's 3 or 3.5 billion parameters. So about half the size of Llama.cpp or a little bit less. It's got a lot of synthetic data, not disclosed. It's a Microsoft model. By the way, Microsoft has a small and a medium, I think around maybe 7, 8, and then maybe 14 billion parameters. Those are stronger models. Also lots of synthetic data. The synthetic data means that it achieves similar performance to models that are trained on larger amounts of data and even of larger parameters, like Llama.cpp, for example, is only a little bit better than Phi-3 Mini. And in some ways, Phi-3 Mini, I think, is possibly better, maybe even in function calling, as you might see here. So let's take a look at how we can use an open source model to do function calling. And in this case, I'm going to do it on a zero-shot basis. I've spent a lot of time on this channel fine-tuning models for function calling, and I think that has historically been a good approach for getting robust results. But we're now, I feel, for the first time, and maybe you could have said this a bit before, at a point where you can zero-shot function call and probably get more flexibility and better results than if you fine-tune. Fine-tuning does tend to restrict the model in certain directions, and if you want customized behavior, and generally applications do have a lot of edge cases, I think zero-shot function calling is at the point where it is the best approach. So let's take a look at how I do this. And it's very similar to the OpenAI script, so we'll benefit from having gone through that first. We import the function tools, so the metadata. We prepare the metadata, the tools.json file. We load the environment variables, and we load the model and the API endpoint, and then the API key. Now, I'm going to run the Phi-3 Mini model, and I'm going to do that by setting up an OpenAI style endpoint, specifically a VLLM endpoint. And the way I'll do it is by going to the Trelis Research one-click LLMs repo. This is a public repo, by the way, so you can access it easily yourself. you will see a list of one-click templates for running VLLM or TGI templates. And the one I'm going to run is Phi-3 Mini. So I'll click on this here. I'll now pick a GPU. It's a small model, so you could pick the smallest GPU here. You could pick the cheapest one. I usually pick the A6000. And you can see I have the Phi-3 Mini template. It's set up and ready to go. This actually goes up to 126K in context, so you could increase that number, but I've kept it down just to save on the pre-allocated KV cache in the GPU. Notice that you do need to disable the sliding window and set trust remote code if you want this to work. So yeah, check out one-click LLMs if you want to run any of these templates. And if you are using Runpod, you can support the channel by using the affiliate link that I provided here, and likewise for Fast AI below. So I've earlier set up an endpoint, and what I need to do is grab two things. I need to grab the pod ID, and I need to inject that back here into the sample env. This time I'm going to be setting it up here with the Runpod API endpoint. So basically I want to paste it in right here. Whoops. Let's go back, copy that and paste it in here. And next I need to set the model. And the model I want to set is the Phi-Mini model. I don't see it here, so I'm going to go across to the template, click edit pod, copy this here, and then I'm going to type in, I'll comment it out for now, model equals, and of course you would need to uncomment that if you're going to use it in production. So here I've set the API endpoint and the model. You don't need to set the API key if you're hitting the Runpod endpoint like this. So now I've set that in the env file as well, and I'm going back to zero-shot func call, and I'm just going to unset in case my OpenAI one is still set. So I'll unset the API key in the model just to make sure. And also I need to unset the API endpoint. Actually, unsetting the API key isn't necessary, because as you can see, if there's no API key, actually, yeah, I should unset it, because that means it will now default to empty when I run this script. So the endpoint is set up, and as you can see, it's the client that we saw from before. This time the API key will be empty, and the OpenAI API base is going to be based on the Runpod endpoint. The functions are going to be loaded as per last time. And now here comes the zero-shot prompting. So let's take a look at this in a few pieces. You're an AI model with function calling capabilities. You are provided with function signatures within tools XML tags. Call one or more functions only if they're relevant to the user's query and are available in the provided tools. So yeah, we don't want functions to be called if they're not relevant. We do want them to be called if they improve the accuracy of the answer. But if there are no helpful functions available, respond directly to the user's query without using any functions. Do not make assumptions about what values to plug in. So you don't want the language model hallucinating the temperature in Dublin. You want it to first call the weather and then use it to get the close. You should call multiple functions in series if needed to gather all the necessary information. So this helps it with series. Before calling a function, verify it's listed in the provided tools. So again, avoid hallucinating functions. Like if you say, what's 1 + 1, it will actually sometimes try and look up a function for 1 + 1. So you don't want it to do that. When the user requires specific information, first call the function to gain the information, then use the info to respond to the user's query. Here's where I'm saying if you can answer the question directly without functions, then give the answer directly. Don't call any functions that are not necessary. On the other hand, if there is an available function that it improves the result, then you should make a function call. I said that already earlier. And here we give the syntax. For each function call, return a JSON object with the function name and arguments within tool call XML tags. And then finally, we give the available tools. Now, I should say that OpenAI is doing something like this in the background as well. I wonder, they may have done a little bit of fine tuning on their model, although they may not, I think, as well, because their models are very good at following instructions, and probably the same for Claude Sonnet, which, by the way, I think supports tool calling too. So yeah, it's possible they're just doing zero-shot as well. As you'll see, it performs really well, even for this tiny model. Much of the rest of the script is the same. Here, loading the functions so they can be called later. Here I've got a script for executing the function call. It's pretty much the same with one key exception here. You'll remember that OpenAI, when it responds, it gives an ID. Actually, we can check that out here. So let's, I know there are a lot of messages, but if we look at a tool call here, so here's the response where there's a tool call, you'll see tool calls, and it's a chat completion message, and it has an ID, a function, and the function has arguments and name. And you see this ID here is generated. It's a unique ID, and when you call it, rather when OpenAI responds with this, you should take that tool ID and you should insert it both where you have the assistant making the tool call and in the response, so that the language model can associate those two. Now, you can train a model to respond with the ID. You can also even zero shot putting in an ID here as well. But I think it's more robust not to put in an ID and rather to just add the ID, if there isn't one, as a random 4-digit hexadecimal number. So that's what I'm doing, and I'm just randomly creating an ID, and then I'm going to take that and make sure it's included in the function call data structure, so that when it gets returned, that ID is something I can include in the function call itself and also include within the response, which I've set up as a dictionary here containing the ID, the name of the function called, and the result. And this, by the way, is the same as before. I'm just iterating through the functions in the functions dictionary and making sure each of them is called. Then we have the recursive implementation. We've a check if we've reached the recursive depth. We've the call to the language model, which is the same. Note though, however, when I use the open source API, or when you use Groq, either the function calling models or not, there is no tools input here. With zero shot, I'm just going to provide the prompt within either a system message or within the first user message. If your model offers a system message, you can put it in there. If it doesn't, just put it in the first user message. That's what I'm going to do with Phi, actually. The rest here is the same logic. Basically, we get the response, we extract the completion text, and then we basically look to see if there's a tool call. And the way we do that is by searching within the tool call tags. And if there's a JSON object within the tool call tags, we load that JSON object. I also have a fallback here. If for some reason there aren't the tool call tags being wrapped, we can try and load a JSON object in case the language model just responds with a JSON object without tags. It actually doesn't really do that, but it's probably worth including as a fallback case. And if there's an error in extracting the JSON, then it's just going to dump the full completion text as the response. And that's going to result in us returning. So we're going to leave the iterations of the loops, and it'll just be like there's a normal response. And yeah, it's important that before I return, I actually append the assistant message that I have dumped. So let me just give an example there. If I say, what's the weather in Dublin? And it responds, but it doesn't make a tool call correctly, and instead says something like, oh, I think it could be warm. That's not going to be readable as a JSON. So we're going to move to this part of the loop here, and we're going to add on that raw message. Okay, so if we do have the case of a function call, we'll iterate through the logic here to execute the functions that are listed. In this case, I'm only supporting one function call. I'll show you parallel later. You'll notice up here in the one-shot prompt, I'm only describing really how to make one call. If I want to give more calls, you'll see this later, I'm going to provide some kind of a structure that looks like this. It'll be an array where I have multiple function calls, and yeah, it's going to look something like that. So this is where it could call multiple calls at once. But in this script, we're just allowing for single function calls, and we have a simple JSON object that's being returned. Okay, so with that, we've gotten to the end of defining our recursive loop. And again, I defined some script for printing things nicely, and then I allow myself to set up the prompts and the tests, and I've got the same tests as before. But notice how there's an extra message here, which is to inject the tool prompt, which contains the metadata. And you can put that in the user role. There is no system role, I think, on Phi-3 models. You could put it in the system role if you're doing Llama, so that's an option. So here we go with the first question. What is 1 + 1? And I'm going to print out, I'm going to get an assistant response, and I'm going to print out the messages I get from that. So let's see how things go. This time we're not running OpenAI func call. We're going to run zero shot func call. And I should have checked, by the way, this needs to be up and running. It is up and running. You can see the GPU is loaded. And if I go all the way, I can't see, but somewhere it's going to say UV corn and running on the zeros port, which means everything is working. So yeah, what is 1 + 1? It's a terse answer, but it's correct. We've got the 2, and it didn't call any function. So it's you can see laid out here, the first user message is that tool prompt we prepared. Yes, I know I'm putting in 2 user messages in a row, and some prompt templates will spring an error if you do that, like Mistral. You can simply remove, if you want, you can just remove that error from the Jinja chat template, or you can just put the 2 messages into the same user message with a few spaces in between, or you can put it into the system message if you like. Okay, and by the way, I've printed out the completion text. If you search up through the code here, I've just printed out the completion text at the end of every loop so that we can inspect and talk about it. So you can see there's only one response here, and the answer is 2. So we'll move on to the next question, which is what is the current weather in London in Celsius? So I'm actually specifying Celsius this time. And yes, we have a tool call, and yeah, you can see it's wrapped in tool call, and we have the ID. Now notice the ID here is present, and that's not because it's auto-generated. It's because I have created a random ID and injected it, and I've injected it as well here so the language model can match the call and the response. And you can see, yeah, it's telling us what the temperature is. Now, interestingly, it is telling us a little bit about what clothes we should wear too, which you could argue is a bit superfluous, but at least it has answered the question that we asked. Next question, I'm giving it the current weather in London, and let's see if it can find the clothes that we should wear. So here we go, and it looks like we've one function call, and we've one response, and yeah, it's recommending long sleeve shirt and jeans. So working really nicely. And the last question is the chained question, where we ask what's the weather in Dublin. So let's see how the model performs on this. And we should have 3 calls. And the first call is to get the current weather. And the next one is to get the clothes based on that. And based on that, it's recommending the clothes to wear. And you can see it's getting the temperature and condition and injecting them for the second tool call. So yeah, folks, it's pretty amazing. I was actually fine-tuning some more models, and I've had pretty bad success with fine-tuning the Phi-3 Mini and also the Llama 3.8B and the Llama 370B. So I said, whoa, why don't I try zero shot? I tried it like a good few months ago, and it kind of worked, but not really good enough. But then I tried it again, and I was also interested in the smallest possible model, and I think this is it. The Phi-3 Mini is the smallest model that, even with zero shot, is able to very flexibly perform well at function calling. And let's even take a look at the parallel function calling, where I've taken it a step further. And this script is really quite similar. Well, actually, I ended up kind of reaching a different place when I was optimizing the prompt, but broadly speaking, it's very much the same, except when we give the syntax for the function calls, we have this syntax here, which actually should have these brackets here. And I've got return an array of JSON objects, and I'm passing in the tools. And notice that I do mention, do I mention parallel? Let's see here. Yeah, I don't think I even need to mention parallel in this script. I'm not saying it's a bad idea. You can include that within the zero shot prompt, but I haven't even included here. And let's see how things go on the performance. So there aren't any other changes. I think the function execution already supported doing multiple function calls. What did need to be updated was when we extract the tool calls, we're now going to be extracting something where the object in between the tool call tags is now going to be an array of functions. And so, yeah, we need to allow for cases where either that's an array and then we need to cycle through the array, or I actually support the case as a fallback where it doesn't give an array and instead just gives one JSON object, not within an array. Other than that, the logic is all pretty much the same. You can see if it's a single function call object, convert to list for uniform processing. So converting that into a list of functions that then we can iterate through. So a little bit more logic there. And now performance time. Let's start off again with what is 1 + 1. And I need to change the name of the script I'm calling because it's parallel. And we'll quickly run through this. So what's 1 + 1? 1 + 1 = 2. And yeah, notice here that it is actually making a function call and it's making it to a function that doesn't exist. So you could argue we should optimize our prompt. However, when it comes back, because I've got this nice error message saying the function doesn't exist, I think that probably helps, and it's still allowing us to get a reasonable answer here. Next, what is the current weather in London in Celsius? So trying this off on zero shot. And yes, we've gotten back the weather in London. Looks straightforward. And you can let me know in the comments if I'm missing anything. Sometimes I do, because I'm moving fairly fast. What is the current weather in London? Or no, I'm giving the weather in London. What clothes should I wear? And here it's doing two things. It's actually making two calls, which you can see extracted like this, which are then being calculated in parallel. So it's actually double checking what the weather is currently in London and then getting the close. So you could argue it's making one too many calls, but it is kind of validating the information, so that's not too bad. And I just want to show you here how it looks. It's actually called with an array of two JSON objects. Next, what should I wear? I'm in Dublin. Expecting here two calls because it's going to be chained. And I think this one, it may have a little bit of difficulty when you try to allow parallel. So let's see. Yeah, it gets the current weather in Dublin and we get the response from that. Yeah, it's not wrong, but it's not realizing that it should be using the get close function, and it's just telling us based on the weather what close might be reasonable. And that's maybe a weakness of my test setup. It would have been better to pick a question like you can tell without calling an API what clothes to wear for given weather. So probably a weakness of my setup, and I should have picked a better second function there. Okay, moving on. What's the weather in Dublin and London? So this is a test for parallel function calling. We wanted to call both, and yeah, it calls both Dublin and London at once, and then it gets the answer and it tells us what we should wear in each. So yeah, this is pretty beautiful. The two calls, you can see them split out there, the responses and the correct answer. And last of all, I've got a parallel series question where we need to find the clothes in Dublin and Madrid. So let's see how it handles this one. And what have we got? We've got, first of all, we've got some parallel function calls. We've actually got 4 function calls. So it's calling for the clothes, for the weather. Let's start with weather in Dublin, which it's giving the correct inputs. Madrid, the correct inputs. It's hallucinating, unfortunately, the close. It's hallucinating those inputs. And for the answers, we've got the correct answers. And it's giving us the answer there, which unfortunately, because the inputs have been hallucinated, that is not going to be a reliable answer. So a few comments on the parallel function calling. First of all, I think you can improve it if you work more on the prompting, particularly if you know you're going to only be doing parallel. It actually turns out doing a combination of parallel and single. Parallel and series can be okay, but parallel and single, getting it optimized for both of those ends up being somewhat tricky. So yeah, more optimization needed to get parallel working. But as you saw in the single calling approach, including with chaining of series calls, the accuracy is really quite high. And what I'd emphasize is the flexibility of the models when you zero shot to handle cases where it asks normal questions. And that's often a case where the models are quite weak. If you have one that's fine-tuned, the fine-tuning can just tip it to be too forceful in the direction of function calling and not be so reliable in the response it gives. Now, this zero-shot script can also be used for very fast inference by using a Groq endpoint. Groq you can find at groq.com, and you should be able to get an API key, and this gives really fast answers because it's running a different type of GPU or different type of computer. I guess they call it an LPU, but it basically has an architecture where they very specifically coordinate the order of the operations to be optimal for a language model. So there's very little time wasted. Every piece of the circuit is being used and the information is not waiting before it moves to the next step. By contrast, GPUs are very programmatic. They have a certain number of cores with certain number of speed, and you take trade-offs in basically shifting the information around. So LPUs, you can think of kind of a custom GPU that's specifically for the order of operations that occur within a language model. And yeah, this is really fast, although it seems probably the API itself is the slowest part. So you can get an API key and you can run models like Llama.cpp or also Llama.cpp, the V3 versions. So that's what I've done in setting up my API keys here in the env file. You want to uncomment the API endpoint for Groq, and you want to also uncomment the API key and then uncomment the model. Now, the model I recommend for zero shot, you can use the 8B or you can use the 70B. They both perform pretty well, as I'm going to show you. And then I'll show you some of the tool use specific models and we can see how that performance compares. But first, let's do the zero shot examples here with Llama 3. Okay, so with my environment variables updated, I'm just going to unset the model, the API key, and the API endpoint. And now that that's done, I can run through these questions. This is the Llama 8B model. 1 + 1, the answer to that is 2. That's great. What's the weather in London in Celsius? Expecting one function call here. And that is not correct. So yeah, even though it's getting the weather in London, it's answering based on the close. I suppose you could argue it is giving the correct answer here. So you could maybe score it as okay, but a little bit distracted on this question. We did see a little bit of distraction on the Phi model too, by the way. Now, if we give the weather, does it get the close? And here you can see it's calling the weather. So it's kind of double checking the weather. I wouldn't say this is a disaster. It ends up as being a reasonable answer. And it does give you the close. So not too bad. And let's test the chaining. So here's chaining. And remember, we're using here the zero shot model. And yeah, you should wear moderate clothing like a long sleeve shirt and jeans. So yeah, this is great. Zero shot on Llama 8B. If you did 70B, it would be even better. But already, like it's actually had the correct answer in each. And perhaps it's a little bit worse than Phi-3. That's what I said earlier. But really, these answers are quite good, and the model's going to be quite flexible because we're not, over fine-tuning it in a certain direction. Now, I'll very quickly show how to use these tool use models. These are custom fine-tunes of the Llama 8B and 70B model that Rick Lammers has done. And thanks to Rick for some help on the review for this video. So I'll run through those. They do require a little bit different of a script because the preparation of the JSON data is a bit different. Specifically, rather than including an array of JSON objects, like here, you can see we have an array of then JSON objects. The way that this is formatted is by putting a new line between the JSON objects. So I actually explained that earlier in the video, but basically take away the square brackets and then instead of a comma here, you just have a new line between them. So that is a small difference. And I think another difference is putting in the tool prompt as the system message rather than the user message. And Llama 3 does support a system message, so that does work fine. Now, note that I'm going to have to update in my .env file to select the tool use model, so I'll do that now. And I'm ready now to run Python Groq func call.py. And yeah, I'm running that chained question first. Didn't mean to do that, but either way, yeah, it gets the weather, it gets the close, and yeah, it gets that answer correct. So chain function calling is working. How about the simple question? Okay, so here it's refusing to answer that question. This is an example of where fine-tuning can make the model a bit less flexible. What's the current weather in London? As a reminder, I'm on the fine-tuned model. So for the weather in London, it asks again for the weather, which is a bit of a repetition, but we saw that as well in the zero-shot model. And then it gets the clothing correct. So it is the correct answer. Now let's see if it gets the clothes if we give it the weather. I'm specifying the weather here. And it does get the clothes. And it gets that answer correct, I believe. So generally speaking, performance also pretty good, but you may face issues in handling these questions that do not require a function call if you're using the fine-tuned model. Now, I'll show really quickly the larger model because there's a larger fine-tune as well. And you can see, actually, I'll just show how if you select that model, it does better on the non-function calling responses. So here I'm just going to unset the model to make sure that's up to date. And let's run function calling. And here it's got the answer correct. Let's check the current weather in London. And it's getting that answer correct. And it's cleaner as well. It's not calling the temperature. It's not calling the weather a second time. Or not a second time, but it's not calling the weather when it already had it. Here it's getting the close correct. And let's test out the chaining. And yeah, so here it's actually not calling a function for the chaining, which is not what we want. So the performance on the chaining is actually not working with the Groq fine-tuned model. So in summary, you see how if I use the Groq setup, I can use either of these fine-tuned models, but actually I probably would recommend trying out at least the zero-shot approach, because if you zero-shot on the 8B, and it'll be even better if you zero-shot on the 70B model, you're able to get probably more flexible and adaptive performance to prompts that don't require function calls, and maybe even overall, you can get better performance on the chain function calling. For the last main section of this video, I want to show you how to run that Phi-3 mini model quantized to 4 bits locally on your laptop. Now, you can run it if you have a Windows computer or Linux, but really it's going to be too slow unless you have a Mac M1, M2, or you have a GPU. Maybe you could look into some inference for some of the newer chips on Windows, and that's something I might look at in a later video. But for now, I'm going to show you running here on a Mac. And the way you can get started with Llama.cpp, which is the well-known library that's good for local inference, you can take a look at the server and API setup and then the Llama.cpp setup. And it will give you the full instructions. For example, you first want to start off downloading the code from Gerganov's repo, Llama.cpp, and then you want to cd into that directory, and you'll then make. Now, actually, you don't even need to add in this Llama metal. You can just type make, and it should compile with metal support, which means that it will use the faster kind of GPU, CPU of the Macs. That's with M1, M2, or M3 chip. You can also do it on Windows, but as I said, it will be a bit slow. Now, when you are doing make, a little tip I figured out is you can put in -J and then 16. This means that you'll have the installation run on multiple threads, and that allows you to go much faster. You can find out how many threads you have, by the way, if you run this command here on Mac. So this is how you make Llama.cpp, and I'm just going to show you now where I have this repo set up. So let me minimize my screen and pull across my terminal here where I'm going to run. So what I'm doing is setting up a server endpoint on my laptop. I'm going to expose it on my local host, and that will be a VLLM OpenAI style endpoint that I'm then going to hit from VS Code. So I'm here in my Llama.cpp folder. I have started up, or rather I have cloned that repo, and then I've typed make in order to make it. And next you can run a few test commands if you like. Let's see if I can do that. So I'm going to scroll down and I'm going to run this test command. By the way, first you do need to download the model. So for example, if you want to download the Phi-3 4K instruct GGUF, you need the GGUF, that's the file type. And yeah, unfortunately the 128K, it's not properly supported yet. I think for GGUF, it's got a weird type of context extension called long rope, which is not standard. So hopefully that will be supported. But anyway, it'll work with 4K context. So you want to go to the Q4. If you have more VRAM, you would need probably at least 16 gigabytes of VRAM. I've only 8, and I probably need, it's probably going to take up about 3 of that. So I'm going to download the quantized one, which is about a quarter of the size, about 2.4 gigabytes. So I've downloaded that and I've put it into my folder in the models folder. So here in Llama.cpp, if I just do ls models, it'll show me a list of the models. And you can see here I've downloaded the Phi-3 4K, mini 4K instruct Q4. With that, I'm ready to run this test script here. It's just a short script that's going to count to 10. So when you run this script, it has to first load the model onto your GPU. That takes a second, and now it's counting. So you can see I've literally put in a raw prompt to continue the prompt, to continue it, and that's why it's got this kind of, you know, repetition thing. I didn't use a proper prompt template, which we will use when we use the server. So to use the server, we want to set up Llama server. And yeah, by the way, this has changed. It used to be just server, but now it's Llama server. Likewise up here, it was main, but now it's Llama CLI. So just be aware of those changes. A few points here. We've got -m in the model. That's the path to the model. So it's in my models folder. NGL refers to the number of layers to offload, number of GPU layers to offload. If you have a model that has like, I don't know, 32 layers, I don't know how many layers are in this model of Phi, it's probably 30 to 50. But you're going to move those layers so they're computed on the GPU. So I've just put in a number that's way more than the number of layers to try and move everything to the high-speed processing. -c is the context. And yeah, just a tip, if you do want, you can use continuous batching on these endpoints as well. You have to put in -cb. Let's take a look here. -cb when you're running the server, and you can determine the number of maximum parallel prompts being processed. So that's with np-16. I'm just going to query with one prompt at a time. So I'm going to run the server without running continuous batching. So let's go back to the terminal and run that. And what happened there? It says server exe. I accidentally ran the Windows command. That won't work. So let's run the Llama.cpp. Okay, so it's setting up the model on the GPU, and all the slots are idle, which is what we want because we haven't made any requests, and it's listening on host name 127.0.0.1. So I think that's my local host. So I'm going to go back to VS Code now, and we're going to hit that endpoint, which is a quantized endpoint. And to do that, we're going to need to comment out Runpod and Groq, which we had been using, and comment in here the AP endpoint, endpoint that we want to use for Llama.cpp. Notice here that this is a way of running either a text generation inference or a Llama.cpp endpoint on Runpod. So you can actually run a Llama.cpp endpoint on Runpod if you really wanted. I mean, it doesn't make a lot of sense because probably VLLM is going to be faster. But if you really want to, you can go to the one-click LLMs and you can click in Llama.cpp. And there's a one-click template for Mistral Instruct. You can modify it for Phi if you wanted, or you can hopefully soon run Mistral Nemo Instruct, although we're pending some support for that right now. So what I want to set here in the environment variables is my API endpoint, and that's going to be on my local host at port 8080. How do I know that? Because it's defined in the Llama.cpp code, which I haven't shown, by the way. And then I do need to define the model as well, because that will be passed in. So we'll move to run the zero-shot function call script now with what is 1 + 1. And let's just unset the API key, the API endpoint, and the model. And then we can run the script. And I'm running here on my local server. So what we should see is if I go, yeah, it's currently processing a task, and you can see something's happening here with the KV cache. So hopefully my video won't smash. And here we have an answer to the question. So looks like it has responded, but it has responded with the right answer inside of some kind of a tool call. So not perfect on that one. Let's see how we can do here on the current weather in London. Now, if this does make a tool call, it will need 2 responses. Notice how things are definitely slower because I'm running on my laptop. This is the smallest model I think you can reasonably run with decent performance. And here we have the response. And it does a good job. It actually gets the weather, and we get the response from the function, and it gets the correct weather in London. Now, notice something up here, and I probably should have shown this a little earlier because it can happen in some cases with the Phi model too. But here's the first completion text. It actually calls the function, but it includes this extraneous text, which is very reasonable. It's saying that it needs to get the obtained temperature and weather first, and then get the clothing. So it's adding extra text, but that's not a problem because automatically our script looks for the first instance of tool call tags and extracts the information. So even if you have cases where the model responds with a pattern like I want to call A, B, and C, automatically we're going to call the first one. So this generally coincides quite well and means that even if you don't have exact response patterns, as long as the tags are there, you're going to get the actual information you need. Now, I'm going to run the other two examples here, but I'm going to do it while I've paused the video because my computer can't take the full intensity with just 8 gigabytes of VRAM. So I'll run both of these and then comment on them. All right, my fan is going mental, but I've run the last two. So let's take a quick look. The current weather in London is cloudy with a temperature of 15 degrees. There's a tool call to get the close, which is what we want. And the second completion is answering with the close. So here we go with the prompt, tool call, tool response, and the correct answer. So really good on that one. And next up, we will look at chaining. So what clothes should I wear? So here we have a tool call. Now there's superfluous information, but that's fine because we'll still just call the tool. And then unfortunately, there's not a further tool call. So if we look at this in pretty print, what clothes should I wear? There is the correct first tool call, but actually it's not even a correct tool call because it should be calling for the weather first, not for the close. And it is actually calling with data that's not useful. So the model is responding back and it's giving useful information to provide that useful temperature, but the model is not actually responding with another function call. So here in this case, in the Phi-3 model, I would say you can use a quantized model to 4 bits and it will work zero shot if you are just doing straightforward function calls, but it's not as strong when it's quantized on the chaining and it's not as strong on the original response. You probably need to be able to run in the 16 bits. And with that, a few final thoughts. We've gone through quite a few models there. To recap, I showed you OpenAI. The model works reliably. If you use GPT4o-mini, it works well with tool use. It's relatively cheap, I think 15 cents per million tokens. And yeah, quality is very good. If you really care about latency and you want 500 tokens per second or 1000 or very high, I recommend using Groq. I recommend using the Llama.cpp model with zero-shot function calling for the best performance. You will get good performance with zero-shot though on the 8B model. And if you like, you can try out as well the specifically function calling fine-tuned models. Last of all, I went through the Phi-3 model. It's a remarkably small model with only about 3 billion parameters, but it's able to do zero-shot function calling provided you keep it in about 16-bit precision. Probably in 8-bit, it would be fine as well. So that's an idea if you want to grab an 8-bit quant. Down at 4 bits, if you run it locally on your laptop, it will do single function calls okay, but it won't really handle the non-function calling response as well, and it doesn't always get the chaining correct either. If you are interested, you could also try out looking at the Mistral Nemo model. That's an intermediate sized model between Llama 8B and 70B. It's not quite as strong, I think, as the 70B model, but it's quite a bit smaller and it fits on a single GPU. So that one most likely would also be able to zero shot. I'm hoping there is support that comes out for VLM for that soon, and I'll make some one-click templates. And that's it for this video on tool use. It's remarkable to me how far the models have come. Maybe I shouldn't be surprised, but just 6 months ago, I was doing zero-shot function calling and was struggling to get the right consistency, whereas now we have models that are smaller than 7B, like Phi-3 Mini, that are able to do this with zero-shot, and I think have great potential to be used on local devices. If you want access to the scripts, you can take a look at trelis.com/advanced-inference. You can purchase lifetime access to the repo or just buy the individual scripts. In the meantime, let me know any questions on tool use or what your experiences have been down below in the comments. Cheers.